This lecture will talk about heat transfer and calorimetry, the last parts that we want to discuss in conjunction with basic thermochemistry, enthalpy, internal energy, things of that nature. And so we have three goals that we want to meet in this discussion. The first goal is to understand how heat can be transferred in chemical reactions or physical processes. So we want to look at not only what will happen if I do a reaction in an area where heat can be transferred, but also what might happen in a physical situation. We won't mention the physical situation specifically because we've done it before, but just be aware that it could be something like throwing an ice cube in water, just the same as it could be a reaction. Goal number 2 will be to measure the heat transfer of the processes and calculate useful information using the results. So we're going to be looking for things like enthalpy and internal energy changes, which are useful to us. And so what we really want to do here is learn to use calorimetry as a tool, not just something to solve problems. And then goal number 3 is to understand the difference in constant volume and constant pressure calorimetry and which of those two things each tells me. One will tell me enthalpy change and one will tell me internal energy change. And we want to understand which one is which and how to look at those two pieces differently. So the first thing we need to do before we can get into this is get a few definitions under our belt, some things that we're going to use, which means we need to know what heat capacity and specific heat are. So just a little background, both of those are useful quantities that we can use to describe the transfer of heat energy between bodies of different heat content. So warm bodies, cool bodies, essentially bodies that have different average kinetic energy values. The first we'll discuss is the heat capacity. It's symbolized with a capital C, and it is defined as the amount of energy required to raise the temperature of the system by 1 degree Celsius or 1 Kelvin, and it's just expressed as joule per Kelvin or joule per degree Celsius. What's important here about this is that the mass is immaterial. We do it for the whole system, and we use that system over and over and over again. If I create a new system or use a new system, then guess what? I have to go back, use a known substance, and determine what the heat capacity of that system is, and then I can use it over and over and over again. The next is specific heat capacity, and we're going to use a small c for this. And essentially, I'm defining it as the amount of energy required to raise the temperature of now 1 gram of a substance by 1 degree Celsius or 1 Kelvin. So now we've taken out the whole, we're looking at a big system, and we're saying we're looking at this particular substance. Now you can have these in different ways. This is really the gram specific heat. There's also a molar specific heat that would deal with 1 mole of a substance, so it really depends on how you want to define it. But in this case, I'm going to define it as per 1 gram. And so we'll add grams to the unit. So now it's not just the energy required to raise by 1 Kelvin, it's the energy required to raise 1 gram by 1 Kelvin. So our units become a little more complicated. And so an example of these are shown below. First, we want to find the heat capacity of a block of lead if it took 45 kilojoules of energy to raise its temperature by 11.9 degrees. If we look up at what heat capacity is, it's energy to raise a certain temperature. So I'm going to calculate that the same way. I'm going to take my heat energy, my Q, or my 45 kilojoules, and I'm going to divide it by the temperature change it caused, in this case 11.9 degrees Celsius, and I'll see that it takes 3.78 kilojoules to raise that block by 1 degree Celsius. Next, we want to find the specific heat of that block if it happened to have a mass of 78.3 grams. So now we want to make it a little more specific. We know it's a lead block, so now I want to see what just lead in general is. And so I can do this one of two ways. I can take my heat capacity and just divide it by the mass, or capital C over M. Or I can remember what capital C is. It's Q over delta T. So I can take Q over M delta T, however you prefer to think of it. But I'm going to go ahead and change my energy in this case into kilojoules, or from kilojoules into joules, simply because the number will be much smaller now that we're dividing by the mass. So I'm going to take 45,000 joules, divide it by 11.9 degrees Celsius times 78.3 grams, and now we see that it takes 48.6 joules to raise every gram by 1 degree Celsius. There is an error here. The kilojoules have been removed, so we can take the K out of here. And so really it's 48.6 joules for every gram to go up a degree Celsius. Notice it's much smaller than this value because up here we weren't reporting it per gram. We were reporting it for the whole block. So it would be 78.3 times higher. So now, looking at goal number 2 and goal number 3, we want to start to look at how do I use these things as tools. Well, the first one that I want to look at, because it's the most common, is constant pressure calorimetry. And so calorimetry basically says that heat flow in has to equal heat flow out. It's a way of applying the law of conservation of energy and the first law of thermodynamics, if you will, to systems under study. And so if we do a reaction in a solution, then the heat lost or gained by the solution has to be the opposite of the heat lost or gained by a reaction that we decide to do in that solution. And so if we look at this, the solution, since it's going to be an aqueous solution in our case, will be the C for the solution, the heat, specific heat, the mass times the temperature change of the solution. That's equal to the heat change for the reaction. Now the reaction is essentially the system, and we're defining the solution as the surroundings. So heat lost or gained by the reaction has to come from or go to the solution. And since we're under constant pressure, we can apply our definition of enthalpy. Heat exchange under constant pressure is enthalpy. So this is going to give us an easy way to measure the delta H for reactions that can happen in aqueous solution, provided that they don't produce large amounts of gas. So just some generalizations. Most reactions in aqueous solutions in a normal lab situation are dilute. So our density is nearly 1 gram per milliliter, just like water under normal conditions. And so whatever volume we measure of that solution ought to be really close to the mass. If we're really worried about doing a high precision measurement, we will measure the mass of the solution, but often we'll use the estimate of the volume. Also, because these things are dilute, the heat capacity of that solution is not going to be greatly different from the heat capacity of water, and so we'll make it just a little less precise. Instead of 4.184, we'll go with C solution in a dilute aqueous solution is usually about 4.18 joules per gram degree Celsius, very similar to that for water. And here's a nice diagram of your standard coffee cup calorimeter. They're using a styrofoam cup. Inside a styrofoam cup for insulation, they have a thermometer for measuring the temperature change in the water, which we're using as the surroundings, and a stirring stick to constantly keep the heat flow uniform so that we don't have hot pockets or cold pockets in the system. When we apply this, we get data from it such that we do a reaction in the water and we watch the temperature change of the water. So here's an example. In a coffee cup calorimeter, we're going to mix 50 milliliters of 0.1 molar silver nitrate and 50 milliliters of 0.1 molar hydrochloric acid, and we know they'll react because silver and chloride get together to form the insoluble salt silver chloride. And so this reaction will happen, and we have two solutions that have been setting in the same location, and their temperatures are both 22.6 degrees Celsius. Once we mix them together, stir them, and allow them to rise to their maximum equilibrium temperature, we note that it's 23.4 degrees Celsius, so they rise. We want to calculate the heat that accompanies this reaction in kilojoules per mole of AgCl, and they're letting us assume that the solution has a mass of 100.0 grams, which would mean that those 250 milliliters that mix together were essentially 1 gram per milliliter, and a specific heat capacity of 4.18 joules per gram degree Celsius. So since it's dilute, both are 0.1 molar, we're applying our approximation. First thing we need to notice is that the final temperatures of the mixture of each solution when we mix them rose. So that means that the solutions gained energy. That means it came from the reaction. So the reaction is exothermic. Second thing we need to note is we're using a coffee cup calorimeter, so the pressure is constant. Essentially, we're working against atmospheric pressure. So under those conditions, we can say that the heat gained by the solution has to be lost or gained by the reaction, which in our case is going to equal the enthalpy. So now we're going to apply our equation and calculate an answer. So since we are at constant pressure, like we said in the step before, what we're going to find is delta H, and it's going to equal the negative Q of the solution because the reaction is doing the opposite. And so it's going to be negative Cm delta T. So if we apply that, we take negative times the C for water, 4.184, times the mass of the solution, which was 100 grams, times the temperature change. All of the numbers here are positive, so my negative outside keeps this a negative reaction. And so that makes sense. We said it's exothermic. It should have a negative heat value for the reaction. And so it looks like this reaction is losing negative 335 joules. That's for the reaction as written. That's not per mole how they request it. And so we need to do a little conversion. So I'm going to take my negative 335 joules and on the fly convert them to negative 0.335 kilojoules by dividing by 1,000. I'm going to look up here and notice that if I use 0.05 liters of each solution at the same concentration, and I have a 1-to-1 ratio here, there is no limiting reactant. They're both in exactly the right amounts. And so if I use 0.05 moles of each, I should produce 0.05 moles of product. And so I'll take my kilojoules, divide it by my moles of product, and see that I will release negative 6.7 kilojoules for every mole of silver chloride that's formed. The next type of calorimetry that we can do is called constant volume calorimetry, or bomb calorimetry. In this case, we are not talking about a solution. We're going to measure the calorimeter as a whole. So the surroundings become the calorimeter. And we're still looking at the heat generated by a reaction. In this case, though, we are not going to find the mass. We're going to look at the heat capacity, not the specific heat. Since the calorimeter, in this case, the bomb calorimeter, is something that's very hard to piece out just the water. It's a system that's sealed and closed. Then we treat it as a whole and look at the heat capacity of it. The only problem is every time I switch to a new calorimeter or get a new bomb inside my calorimeter, I have to recalculate the heat capacity by using a known amount of substance. So in this case, it's still going to be negative. It's the opposite, but we're going at constant volume. And when we're at constant volume, that means we're looking at the change in internal energy. This has to do with the fact that work, if you remember back, delta E being equal to heat transfer plus work. Well, in this case, no work can be done. If I'm at a constant volume and I'm doing a reaction inside here, and the only thing inside my container is going to be gases, which is going to be the case here, then I'm limiting the amount of work that can be done. As a matter of fact, we use this to investigate primarily combustion reactions because they produce large amounts of gas. So since I'm in a bomb, I don't allow expansion, which is the only work a gas can do. So the work goes to zero. And so all the heat energy is the only thing going on, and that's the change in internal energy. And again, we mentioned we're using heat capacity, and we mentioned that we're measuring change in internal energy since work is not allowed. Here's a quick picture of a bomb. It's pretty complicated. Notice they're still measuring a temperature change in the water, but it's all a sealed unit, so it's very hard to piece this out. And the reaction is happening inside a sealed box, which will heat and then heat the surrounding water. So here's a sample for this. Notice the first thing I've got to do in part A is find the heat capacity of the bomb. To find the heat capacity of the bomb, I look at a known reaction. So they're telling me I burned 6.79 grams of methane, and I know that methane releases negative 802 kilojoules per mole when it reacts. This causes my system to rise by 10.8 degrees Celsius. So to calculate the heat capacity of the bomb, I just take my heat and divide it by the temperature change, just like we did earlier. My heat, though, is a little bit more complicated. I have to find it by taking my 802 kilojoules and dividing it or multiplying it by the 6.79 grams, which then needs to be converted to moles. And so I've got kilojoules per mole times moles divided by the temperature change shows me that I get 31.51 kilojoules per degree Celsius. Notice the C is positive. The delta H was negative, but the C is positive. The calorimeter rose in temperature. Next, I want to take what I know about this calorimeter and see what a reaction does. So I'm going to take a 12.6 gram sample of acetylene, burn it inside that same bomb, and inside that, when that's burned, it raises the temperature by 16.9 degrees Celsius. And so I'm going to apply my delta E equation since we're at constant volume. The heat capacity of the bomb is so that every time it goes up by a degree Celsius, that means 31.51 kilojoules of energy has been absorbed, and I rose by 16.9 degrees Celsius. So that reaction gave off 533 kilojoules, hence the negative sign. It's combustion. It's exothermic. Should make good sense. But that's not how they want to see it. They don't want to know it just for this reaction. They want to know it in kilojoules per mole of acetylene. So I've got to do some work. I know those 533 kilojoules of acetylene came from 12.6 grams of it. So now I need to do a quick mole conversion. 1 mole of acetylene is worth 26.04 grams. And that shows me that this reaction releases negative 1.1 times 10 to the third kilojoules per mole. I'm sorry, releases positive 1.1, or if I'm just going to write it, I'm going to say it's negative 1.1 or negative 1100 kilojoules per mole. And that is how you handle calorimetry.